Oh dear. Oh, it's hot outside. Okay, alright, hat off. Let's get on with the show. Today, we're going to learn some things about operational amplifiers, and in particular about the slew rate involved with the operational amplifier. But what is this thing called slew rate? Well, slew rate is to do with the speed of change of the output voltage in the operational amplifier. I've got here this robot which you may have focused your eyes on and wondered what the heck has he got this little robot here for. Well, the robot can also slew. If I slew the arm of the robot around, it takes a certain time to travel the distance from one point to another point. And this is just like our operational amplifier. The operational amplifier needs time to transfer the voltage from one point to another point at the output of that amplifier. And if we try and transfer that voltage too quickly in the amplifier, we'll get distortion. If we move the arm on the small robot too quickly, the small robot will topple over. And you know, in industrial applications, this is really important also because big excavators working on building sites that are using the arm and slewing it around, carrying a bucket full of spoil, if they slew the arm too quickly and they're on the side of a hill, the inertia of the arm and the weight contained at the end of the arm can easily make that machine topple over and have a very bad industrial accident. So this term slew has to do with how quickly we transfer something from one point to another. It has to do with movement. So I'll just move our little toy robot out of the scene. He's done his job. Look, behind me I've got some very rough board notes where I've done this in class already today. We considered the inverting amplifier with the op amp at the center of the picture there. There are two ways we can wire this up to act as an amplifier. It can operate in the inverting mode or in the non-inverting mode. They're a whole different video entirely. And there's probably a stack of those already on YouTube. In here today, like I said, I'm going to feature slew rate. The slew rate of the amplifier is quite important. It's a characteristic which is found in the specification sheet for the particular op amp. Some operational amplifiers have very fast slew rates, like 70 volts per microsecond. Other operational amplifiers have extremely slow slew rates, which are down around about 40 millivolts per microsecond. And the UEENEEH139A operational amplifier, the specification sheets tells us that it's about 0.5 volts per microsecond of voltage change at the output of that amplifier. Well, one of the labs which we've done today had two operational amplifiers in a Cascade configuration. We set the resistors, the RF and RIN, 22K, 1K respectively. That gave us a gain of 22 times in each stage. With cascaded amplifiers, 22 times, we've got to multiply those together to get the overall gain. I've done that and I got a gain of 484 times. I'm running the split rail on each of the op amps, minus 15 volts, positive 15 volts, and I need a headroom in my operational amplifier. If I do not allow enough headroom there, we'll get clipping on the output of the amplifier. So the headroom in the specification sheet for the 741 is 1.5 volts, and therefore I've set this to be just 24 volts peak to peak for my signal at the output with 30 volts of total rail voltage. That way I've doubled the headroom. I've got 3 volts of headroom on each side, haven't I? 3 and 3 is 6, 6 from 30, 24. So there's no chance of me getting any clipping. That's the last thing I need. And this amplifier is going to be working quite hard to give me 24 volts peak to peak. The amplifier in front of that, stage 1, stage 2, stage 1, not working anywhere near as hard. The peak-to-peak waveform at this point just 1.09 volts peak-to-peak with the same RF and RIN. the overall signal that I can put into this before I start to get some distortion at the output, and keep it within that 24 volt frame, is 49 millivolts peak to peak. And that's pretty easy to work out, just 24 volts peak to peak divided by 484, the overall gain of the amplifier. But clipping is one thing. What about this slew distortion? And I've drawn a bit of a triangular waveform here on the output of the amplifier. Well, slew rate, like I said, represents the maximum rate of change for the output voltage and the frequency maximum, which I can employ with my operational amplifier, because frequency is the speed of operation for the change of voltage, is going to be the slew rate divided by 6.28 times VP. And my peak voltage here, given that I've got 24 volts peak to peak, will be 12 volts peak. So taking that maths a little bit further, 0.5 volts per microsecond given to me in the op-amp specification sheet, divided by 6.28 times 12, breaking that down, be 1 on 6.28 times 12 multiplied by 0.5 divided by 1 microsecond, and that'll give us 6.6 kilohertz. So below 6.6 kilohertz, I haven't got any risk, supposedly, of getting slew rate distortion at the output of the amplifier. But if we go over the frequency of 6.6 kilohertz, and we're pushing the signal to such a large extent, we're nearly at full rail on the output there, we're asking for a lot. It's a fast change over a large voltage, and we're going to get some severe distortion. Alright, look, we'll go to the bench now. We'll have a look at the amplifier wired up on the bench, review quickly what we've talked about, and then we'll have a look on the oscilloscope at the slew rate distortion as I go higher in frequency than 6.6 kilohertz. I'll go below it, maintain 24 volts at the output, we'll see a nice sine wave. At that frequency, we might just be starting to get a bit of distortion, I'm not sure. And then as we go over 6.6 kilohertz, we should see some pretty rough looking waveform there that doesn't really resemble much of a sine wave anymore. Alright, let's go to the bench now and have a quick look at that in operation. Okay, here you can see clearly the setup that we're using today. We've got the two 741 operational amplifiers, and we do have a split rail power supply unit. So I've got 15 volts positive, 15 volts negative, with a common 0 rail in between the two. So I'll zoom in and we'll have a closer look at the amplifier proper, and then we'll go to the oscilloscope waveforms and the frequency comparisons to have a look at that slew rate. Well, we're on the bench now and we've got the circuit set up. Here's the first operational amplifier, followed by the second operational amplifier. So that's stage 1 and stage 2. The stage 2 amplifier is the one who's doing the most work here, because he's really trying to push the output level to quite high levels. Now, what we'll do, we'll take the camera and we'll have a look at the oscilloscope and get an idea of exactly what's happening with this circuit. Remember, we were putting in about 50 millivolts peak to peak, and on the output channel over here we should be expecting to get about 24, 25, 26 volts peak to peak before it starts clipping. Alright, I'll just spin the camera up now to the oscilloscope. So I'm using channel 2, which is in blue, for the input. The input is set for 20 millivolts per division, peak to peak. You can see here VPP, VPP. It's important to make sure that the settings on the oscilloscope have been set up to read in peak to peak. So we've got about 46 millivolts peak to peak. I mean, I'm so familiar with an old oscilloscope looking at the screen and going per division, but I guess I am getting lazier these days. 46 point something, 47 millivolts input. The output setting at 22 volts peak to peak. So I'll turn the input signal up just a little tiny bit. 50 millivolts peak to peak, and we've still got no clipping at the output. Oh, there we go. So at around about 60 millivolts peak to peak at the input, we're all of a sudden getting negative peak clipping on the output. And then if I go up much higher, we're not quite symmetrical there. We got clipping on both top and the bottom of the waveform. At the moment I'm running with 6 kilohertz of signal input frequency, and I've got no slew rate distortion apparent in the output. I'll just spin the camera around and we'll have a look at that signal generator. There it is there, 6 kilohertz. And then what I'll do, I'll increase the frequency now from 6 kilohertz going up 7, 8, 9, 10, 11. I reckon by 11 kilohertz I can see with my eye that I've got some distortion happening here on the screen. Look, this is still rounded. This has got quite a sharp peak on it. I can stretch it out a little bit. Now I have got a small phase difference here, of course, between the input and the output signal. So even when I raise the output signal up here to compare it with the input, it'd be nice if I could have put the input directly over the top of the output there and look at the shape. But I can see that I'm more rounded there on the input than I am on the output, meaning that we're starting to get some slew rate distortion. The output can't quite change frequency, can't quite change the voltage. The voltage swing can't happen quick enough without causing me some distortion. So that's at 11 kilohertz. I'll go now a little bit higher in frequency again. And can you see that? Oh, look at that. I'll just try and maintain the... No, I can't even push the output anymore. I can increase the input voltage to the amplifier, but the amplifier has really, can I say, jacked up at that stage. I'm putting in even 75 millivolts peak to peak of input signal, but look at this. I've got a beautiful triangular wave coming out now at 15 kilohertz. So not only did we get the slew rate distortion happening there because the op amp can't track that frequency quick enough, but we can't take the output any higher now than 23 volts peak to peak. It's just said, nope, I've had enough. And back down to 11 kilohertz, I can still see I've got distortion. Oh, now we've got, all of a sudden the amplifier's sprung back into life. It's decided that the slew rate distortion's not so bad. It's trying to do some amplification, but now I've got flat topping, so I'll have to turn that input back down again to 49 millivolts. 50 millivolts will do. I'm at 9 kilohertz now. I'll come back down to 7 kilohertz. And of course we've got a perfect signal. I can't see any distortion there at 7 kilohertz. I reckon I could see it with the naked eye probably from about, there's 10 kilohertz. I'd say 10 to 11 kilohertz. That's 11 kilohertz, 10 kilohertz. I can see that I'm starting to get some crook looking signal there on the output already. Now I'll go back up to 16 kilohertz, and we've got now that horrible looking signal. And what I'll do, I'll bring the output back down here where we can separate it away from the input, and I'll turn the gain of the amplifier down. Oh, look at this. Whoa. Look at that. Now I've only got at 7 volts peak to peak, 8 volts peak to peak on the output. At 16 kilohertz, I don't have a problem. Why don't I have a problem? Because I'm not pushing the output stage to get that large voltage swing. I'm only taking 7.7 volts peak to peak now. So I'd have to, where I had 12 volts peak in my equation before, I'd have to take half of 7.7. So let's call it a shade under 4, 3.8 volts or something like that. I'd have to put that into the equation, and we'll do that, and we'll find that the frequency of operation will indeed be much higher. Okay, I've just done the new mathematics on that. I've put in 3.8 volts peak instead of 12 volts peak into my equation, and now it's telling me I should be able to go to 21 kilohertz safely before I start to get slew rate distortion. So let's try that. Let's see if it works. We're currently looking at 16 kilohertz. The mathematics tells me I should get 21 kilohertz before I get slew rate distortion. So look at that. We've got 16. We'll up that a little bit, take it to 21. I can't see too much evidence of distortion there. It's kind of looking a little bit peaky. I'll go a little bit higher. 21, 22, 23, 24, 25, 26. We are shrinking down in output, so I probably should increase the output level a little bit and try and keep up to where I was. I'm not seeing the same evidence. Okay, I've certainly got slew rate distortion there. Look how peaky that is. But let's look at the frequency I'm at. I'm at 37 kilohertz. The mathematics told me over 21 I'm going to start to get distortion. I think I haven't done too bad. That is quite severe distortion. A distortion analyzer would be what we need to see where the distortion starts to kick in. Again, it would have been nice if I could have put the two waveforms together there, but I have got that phase difference. If I could have got the waveforms at the same level, anyway, I'll use that vernier function there. Yeah, look at 23 kilohertz, I can't see any impact on that. I'll have to up the input again. Oops, no, it said I'm not going to go any further, and there you can see we've got our distortion there at 30, 36, 37 kilohertz. Quite a bit of output distortion caused by slew rate. Okay, bring him back down again. Oh, where are you, critter? There he is. Very pointy there. 37. I'm running 48 millivolts peak to peak at the input. I'm down to 28 kilohertz there. Ooh, 22 kilohertz, but the output is humongous. Yeah. There we are. That's the problem. Once I turn that output down, the voltage swing on the output, it's not working the amplifier so hard, so the change in voltage over the change in time is going to be less than it is when I had that really big output. So that pretty well wraps up what I wanted to do. We've had a good look at slew rate and frequency and output voltage, and we've seen that if we do push our little op amp that little bit too far and we have a big DVDT, a big change in voltage over the change in time because of the higher frequency at the output of the amplifier, we're going to get quite severe slew rate distortion. And if we don't have slew rate distortion but we push the amplifier too hard, we'll go into the headroom and we'll actually get clipping, which we saw at the beginning of the practical part of the video. I hope this has been a good video. I do put a lot of work into these videos and try and make them good. This is Greg Moore for New South Wales TAFE. Thank you. get more than about.
Yep.
Before I had 24 or 25 volts peak to peak on the output. I can't get as much now because the poor little critter's gone. I surrender. Go away. Don't do it anymore.
Give it up.
If I turn the output down and I don't have as much DVDT, then again, perfect, absolutely perfect. So, yeah, real good. Fun and games.